Guys, how you doing today? I just want to talk about barometers and how we measure air pressure. As you can see on my watch, the barometer reads 1011. That's in millibars of mercury. So I want to start off by saying 1 bar is almost 1 ATM. 1 millibar of mercury, that's milli, 1 times 10 to the negative third, is 100 pascals, or 0.1 kilopascals. Okay. Atmospheric pressure is usually 101.3 kilopascals, or 14.7 pounds per square inch at sea level. Okay, I want to give you guys an example. Let's say we have a big container, a huge container full of water, and the height is, or the depth is, 10.5 meters. The pressure at any point along this, inside the container, is going to be rho GH. I also want to note that gamma is rho G, which is density times gravity. Rho GH and gamma H is basically the same thing. In hydrostatic, let's see. In hydrostatics, this water is going to exert a triangular force, or it's supposed to be a straight line, it's a triangle. It exerts a force on this wall. The centroid of this force is located right here, about 1/3 the distance from the bottom. So the force on this wall is going to be the area of this triangle, which is 1/2. The base of this triangle is rho GH. 1/2 base times the height. The height is h, so the height is going to be squared, times the width going into the board, because this is the elevation view. So into the board would be the width. Times the width. In US units, this is metric, but you can also use it in US. But in US, it's easier if you use gamma. Gamma H squared times the width, and the force is going to be in newtons or pounds. But let's say we don't want to measure the force on the wall. We want to measure the pressure at the lowest point of the tank, which is going to be rho GH. In metric, it's going to be, the density is going to be 1,000 kilograms per meter cubed, times the gravity, 9.81 meters per second squared, times the height, which is 10.5 meters, times the width. Let's just say it's going to be 1 meters in width. Okay, as you can see here, I'm sorry, you don't need the width here. I was thinking about the force, but this is just rho GH. Rho GH. If you check the units, we have kilograms times meters per second squared. This term right here is newtons, which is mass times gravity. So we got newtons divided by meters cubed times meters. So that's newtons per meter squared, which is pascals. 1 pascal is 1 newton per meter squared. So this whole expression right here is going to be about 101.3 kilopascals. So atmospheric pressure is equivalent of being underwater 10.5 meters. Let's do this in US units. In US units, we're just going to use gamma. Gamma H is the pressure. Is the same thing as rho GH. So gamma water is 62.4 pounds per cubic foot times the height is going to be, well, 10.5 meters is about 34.4 feet. So the feet cancel, so it's going to be pounds per square foot, but we want to move it to pounds per square inch. So 1 foot is 12 inches, but we have square feet, so this is squared, this is squared, sorry, so this is squared. So 62.4 times 34.4 divided by 144 is going to be about 14.9 pounds per square inch, which is close to 14.7 psi and atmospheric pressure at sea level. Okay, I want to also talk about a little bit about fluid mechanics. Let's say we have a pipe with a fixed area and the area stays the same. Flow equals velocity times area. And let's say there's a bend right here, and let's say we have a water in the pipe and it's flowing this way, then it hits this wall, and then it moves down. So we want to know what the force on this wall is. So the force exerted upon the wall is going to be the density of the fluid times the flow times change in velocity. Change in velocity is the final velocity minus the initial velocity. We can say at this point that the velocity is going to be 0 to be conservative. So the change in velocity equals negative initial velocity. So this term is going to be negative initial velocity. So this whole term is going to be negative, but it's still going to be the same number, but it's just going to be negative. You're just going to know that it's a force. Okay. Or you can also say that the force is going to be rho v a velocity squared. And if you want to know the pressure at that point, which is force divided by area, just divided by the area, gets rid of this term, and you got a rho v squared as the pressure. Let's do this in SI units. So we have 1,000 kilograms per meter cubed density of water. The density of water changes with temperature. We're just going to say it's 1,000 times the flow. We're just going to say that the velocity is 1 meter per second and the area is 1 square meter. So the flow is going to be 1 cubic meter per second times the change in velocity, or the velocity, we're going to say it's 1 meter per second. As you can see here, we have this meter cubed and this meter cubed cancels, and we have 1,000 kilograms times meters per second squared, which is 1,000 newtons. And in US units, it's a little bit different because we have gamma of water at 62.4 pounds per cubic foot. So in US units, you have 62.4 pounds per cubic foot. You gotta divide that by gravity, 32.2 feet per second squared, to get the density. Well, it's gonna be in slugs per cubic foot or so, times the flow. We're just gonna say that flow is going to be 1 cubic foot per second, even though 1 meter cubed per second is not the same thing as 1 cubic foot per second, and it's the same thing with the velocity. But for this example, I'm just being lazy and I don't want to move the units around, so I'm just going to say it's going to be 1 cubic foot per second times the change of velocity, or velocity. It's going to be, I'm also going to say it's 1 feet per second. I just want to stress that 1 meter per second and 1 cubic foot per second is not the same thing as 1 foot per second and 1 cubic foot per second. I'm just being lazy. So we have here, this is pounds per cubic foot. So this cubic foot cancels with this cubic foot, this foot cancels with this foot, this second goes on the top, so it cancels with these two. So all you're left with is pounds. Sorry, I don't have the best handwriting. So your force is going to be in pounds. And I also want to talk about detention time. Let's say if you have a faucet or a garden hose or your sink, and you want to calculate the flow in your sink. I'll give you an example. Let's say you have a container and you have an influent going in, let's say water coming in. It's going to come to a point where it's going to start overflowing, spilling out. Effluent and influent. So the detention time is going to be volume divided by flow. And you got to watch the units. You got to be careful with the units. So in metric, we'll just say that the volume is going to be in cubic meters, or it can be cubic centimeters, or divided by flow, which is going to be meters cubed per second. You want to make sure that the detention time is going to be in seconds. You just want to make sure that the units cancel out and it leaves you with time. So if you know the volume of your container and you record the time it takes for it to fill up and overflow, then you can find the flow.